All right, so lovely to be with you, ladies and gentlemen, today. What I would like to do is make sure that we understand why we're going to be experiencing the things we're experiencing. What is this technique that we call chromatography? Why are we doing a chromatography experience now in our course? So how does it relate to what we're talking about? The goal for today, so I know I gave you 2 packets. Everybody have 2. So we should have this that just says paper chromatography, and then another one, a laboratory introduction to chromatography. We're all good. So first, this paper. I want to make sure we understand the theory. Then we'll transition into, okay, what are we exactly doing in this lab? Oh, did I give you 2? I'm sorry. I'm so sorry. Who knows? One extra one for good measure. Okay. And then we'll talk about the goal that we have. All right. Could I ask you to please first, on your own, read what I have highlighted here, the background. Go ahead and read that, please. All right. Yesterday, we each had our piece of filter paper that we deposited and made our initials or a smiley face with the same color pen, different color pen or markers. And then we exposed this to drops of ethanol solution. All right. We experienced different things. So in this exercise, how is that reflected here? All right. In chapter 1, we talked about classifications of matter. And one classification is mixtures. Nathan, can you give us an example of a mixture? Oh, well, that would be a specific type of mixture. I wouldn't say that's an example of a mixture. So if you think about the world around you, what would be an example of a mixture? Yeah, chocolate chip cookie, which would be homogeneous? Heterogeneous. Very good. A chocolate chip cookie. And let's just say, which I can never imagine this, quite honestly, if I can be so bold to say, maybe it's not a chocolate day for you. I can't imagine that ever happening in the world of Gerhardt. I love chocolate. Anyway, let's just say your chocolate cookie, you're not feeling chocolate. You could just pick out the chocolate or chocolate chips or eat around them. Yeah. We know that mixtures are just physical combinations, and physically we can separate them. Tossed salad. 2 of my 3 kids still are not fans of tomatoes. And they keep reminding me, Mom, you can keep putting them there. I'm so sorry. Not going to eat them. So they eat around or they pick apart. Easy peasy physical separation. Sand in water. You could just pour that into a filter, yeah? And you catch the sand. But not all mixtures are that easy to separate. That's what we're going to be faced with today. So for example, Sharpie. How does Sharpie make the black ink? Does it combine different colors? Or is there a black specific molecule? Or how about this shade of green? Is this an individual color molecule? Or did Sharpie combine a little bit of maybe blue with a whole lot of yellow and so on? So we're going to investigate marker and pen inks, but also, Mrs. Kendrick and I thought, be a little extra interesting if we investigated What does M&M use to make the different colors that we enjoy? So we're going to look at those kind of colors as well. So that's what we're doing. All right, so yesterday you did this. We are trying to investigate, are there separate parts in the mixture? And can't really pour them through a filter or pick them out with forceps. So let's try chromatography. And chromatography, Logan, separates using a stationary and a mobile phase. So yesterday's adventure, what was the stationary and the mobile phase?
Was the stationary the paper and then the mobile?
Gosh, jackpot. Yes! My morning class kept saying, oh, the markers were the mobile. No. The marker is what we're trying to investigate. That's our test substance. So here, the purple bled. And we ended class with this yesterday. So today, we are going to use polar paper. That'll be our stationary phase. It's very similar to the filter paper. It does get a special name, chromatography paper. You'll see ours is a bit more rectangular just because of the testing that we're going to do. We are going to be a lot more purposeful and disciplined in how we prepare our samples instead of just, writing our initials, and actually collect some measurements with it. Okay, so if we could now transition here. We're going to alternate between these two different packets. So just to jump right in, we're going to be separating food dyes and also marker and pen inks, looking at their different responses to stationary and mobile phase. And we'll talk more about that as we talk about the procedure. There's two things we're investigating. One are food dyes. So could I ask you now to read 1, 2, and 3, and then we'll talk about it. 1, 2, and 3. There are 6 different colors of M&Ms. The second page of the procedure packet has your data table. Here are our 6 colors. So what I would like us to do is share the dye prep with a lab group that's close to us. So if we want the members at this table to team up with that table, this table with that, and so on and so on. Each lab group will make 3 of the 6 dyes. 3 of the 6 dyes. So if you want to say, okay, I really like red, yellow, and orange. So I'm going to make those and then tell the other team, go ahead and handle the others. The samples that we need are here. So I'm going to place the chromatogram paper on Kanan's desk for us. So you are going to take one of these plastic Dixie cups, one for each of the colors that your group is going to make. And how many M&Ms are we using?
3 or 4.
3 or 4. Yep. So you're going to get 3 or 4. Now, if perchance there's a broken M&M please go ahead and toss it. So I tried to go through and separate all the broken ones. And by broken, I mean it has the chocolate exposed. Just go ahead and toss that and don't use it as one of yours. We are going to expose these to that same ethanol mixture that you used yesterday with your initials. That will dissolve away. And M&M is, of course, the delicious chocolate center. But then they immerse it in a white actual candy coating that helps preserve the chocolate and separate it from the food dye and helps the food dye to stick. Then there's actually another sugar coating that's just a gloss. It makes it kind of shiny. We want to dissolve away the glossy, that's just colorless, and then allow the food coloring to dissolve. But we don't want the chocolate to dissolve in some of the ethanol solution. So keep an eye on it. I have bottles of that ethanol solution at your station. You will just 3 to 5 milliliters. You'll add, and just pour it in, so it covers the M&Ms, just covers them. Then it'll be the concentration of the food dye that will really give us good results. So you pour just to cover, just to cover, just to cover. Give them a swirl every once in a while. And then when you start to see that white, I have forceps at all of our stations. So, and to ease cleanup, I would get a paper towel, set that to the side, and then just so that's easy to throw away with your M&Ms. The M&Ms, I cannot even predict how old they are. They're old and they've had many hands in them and they've been sitting out. So we know we never eat anything we're using in lab, but especially these. So if you're thinking, I'm just going to sneak, no. Ugh, yuck. All right. Once you're hardly seeing any of the color any longer and you see that exposed white, you'll just take out then the core, but you have your beautiful dye solution. All right. Also at your station is a beaker that contains capillary tubes. Capillary tubes are just really narrow straws, if you will. And these are glass. The original capillary tubes were about 6 centimeters long. You don't need them that long. So I broke them. So be careful because one of the edges will be a little sharp. So whenever you're grabbing them, definitely handle them from the middle. And you'll get a capillary tube for each of the colors. So you've taken all the M&Ms out. Now you're ready to prepare your chromatogram. All right. The chromatogram paper is over on Caden's desk. And I have one ready. And the directions talked about putting a start line. It said 1 centimeter. I suggest placing that 1.5 centimeters up. Okay, it's good if we give a little more distance between your samples and the base. All right, there are 6 different colors. So we're just going to space them out. You don't have to measure these. But what we should do is identify, okay, where did we put that to start? And let's say I'm going to put my yellow. So I'm just going to use a Y to be yellow. Feel free to write yellow. Feel free to number it just so that you remember, oh, that was the yellow. And then we have the orange and then red, green, blue. Oh, I probably don't want to use B for blue and brown. So just designated differently. All right, and what you'll do, I know we all think the more the better, or the bigger the better. Not so. We just need a small, concentrated enough sample to start. So capillary action, that's why we call these capillary tubes. You don't have to do anything other than touch the capillary tube to the solution. And naturally, because the solution dye is polar, water is polar, glass is polar. It will naturally move upward and fill part of the capillary tube. So you'll pick up some liquid, and then all that you're doing is just touching it ever so lightly to the mark that you made. Then it's up to you, but you can just put that back in because you'll need to share this with the other team, but also to make repeated applications like the procedure read. So you'll do the yellow, the orange, the red. If you want to switch with the other team, or just give this a wave. The alcohol will evaporate and be encouraged to evaporate with waving around. And if you kind of wait and wave it 30, 40 seconds, then you're ready to make your next application. And so on. So what you'll end up with is this beautiful color spots. If while you're making the application, oh, a drop comes out, well, just get me to take a look at it, because where that drop fell, we may have to make another spot or something else. And the only thing to make sure we're doing is not putting our samples too close to the edge. Once you have all of this prepared, oh, and I can't believe I forgot to say, we are definitely marking in pencil. Pencil will not move with the mobile phase, so it will stay where we put it. You want to make sure that you are marking the chromatography paper with initials. Okay, all right. So then I'd like us to keep the staplers up here. Then you come to the stapler, because if we take things back to our station, sometimes they just get lost. So you just create a cylinder, but we don't want to overlap the chromatography paper. So what you'll do, and I will be an extra set of hands for you, we will staple it such that it is not overlapping, but yet held as a cylinder. You see there's a gap there. We don't want them overlapping, but it's held together so that when you staple the bottom and the top, okay, then it will hold like that in the developing chamber. Questions on applying our dyes, preparing the dyes, getting that cylinder ready. Okay, so that's our stationary phase, and we have our samples. At each of your stations, I already have a large beaker that contains the salt solution. So number 4 says add 5 to 10 milliliters. It's already added for you. It's already ready to go. The beakers have parafilm covering them. Parafilm is the greatest saran wrap. It is non-permeable. It doesn't allow stuff in, and it won't allow stuff out. When it's stretched, it gets sticky, and so if you just push on it, it'll stick to the beaker and then seal it. So to open, just gently pull off. If it rips or anything, just let me know. I'll get you a new piece. No worries. But what you'll do is then take the cylinder and lower it into the developing chamber. We don't want to disturb it while it's developing. So if setting it there will be in your way, set it over here. You don't want to move it or rock it when the chromatography paper is in there, because then that could cause some bumpy mobile phase movement. So we'll just set that in, gently put the parafilm back. You're welcome. And then we just let it go until the mobile phase is about 2 centimeters from the top of the paper. That will definitely give probably the time it'll take once we're in our stations, at least probably 15 minutes to do all of the measurements we need. Okay. Questions at all? You can just look at the screen, or if you would like, we can go back to this paper chromatography packet. Now, we'll see. We will see. But your dye will end up being a kind of, I don't know, a bunch of blobs. And so the question is, as the mobile phase travels, is whatever M&M uses for the blue dye, is that more attracted to the paper or attracted to the mobile phase, or kind of half and half? As the liquid moves, you'll see traveling and possibly separation. So for example, let's say green. Let's say M&M uses blue and yellow to make green. So you may observe that, maybe after a couple of minutes, first the green is traveling together, and then you start to get a blue kind of spot, and then a yellow spot. Okay, so we're going to get a series like is on this packet of dots. Okay. Whenever you are ready to take your cylinder out of the developing chamber, I suggest put a paper towel down, because this will be wet and it'll just help with cleanup if you set it then on a piece of paper towel. The liquid will have traveled through, and what we need to do, the directions say, is trace how far the liquid did go whenever you took it out. Just lightly make that. If a hole develops in the chromatography paper, no worries at all. You're also going to make a mark in the middle of each colored blob, if you will. So I'll judge that to be the middle and that to be the middle. Maybe the blue, I'm sorry, I'm using the same color, made a blob like that, and maybe there's some like right there. So I would judge right there and right there. Okay. Everybody's chromatogram is going to be a little different. Your liquid level may start a little bit different. There may be a lot of foot traffic around you, so it makes it bump a little. Maybe your application, is a little more concentrated than someone else's. So from team to team, they will not be identical, but incredibly similar. But what should be on point is what we measure to calculate. Okay. We're going to have different distances of solvent travel. But how do we know if the green on my M&Ms did the same thing, the same exact thing as Abby's group or Aaron's group or Mary's group? Well, that's where what we call the RF factor comes in. Okay. There are rulers at all of our stations. We are going to measure what we need here. All right. You don't have to, but I'm going to show you. In the procedure packet and our data table. Okay, so let's say the green. I'm going to show you an example of what I would do. So the green M&M, the dye color, I got 2 different colors. So I'm just going to divide this into 2. And this, remember, we want to go more descriptive than just base color. So this, I'd say a navy blue. And then I'm going to say that's a bright yellow. All right. And then the distance the spot traveled. So what you are doing is going from start to the middle for each of your blobs. Sorry, I'm just calling it blob. Each of your separate, results. So I would say, remember, sig figs with our measuring tools. We can go to the 100th place, so 0.94 centimeters. Now, the table reads millimeters, but you are fine to be in centimeters. But if I'm going to do centimeters, I'm going to change that. Okay. And then for the yellow, I do from start to where it ended. And so that will be 5.62. Then the distance the solvent traveled. So for that, let's just say 9.68. And it's going to be the same for both. So I could write it again or just realize it's the same for both. The RF factor is the ratio of how far did the blob go versus how far did the solvent go. And here's an example. Notice no unit. It's just a ratio. Be careful of sig figs. Food dyes actually glow when exposed to ultraviolet light or black light. However, we need to not have any visible light. I love our windows. Our old classroom made this very easy. I'm figuring it out. So for today, you're not responsible for measuring fluorescence. So we can leave the first column and the next to the last column blank. Okay, we will do that for all of the M&M samples. These are going to be wet. We are not together enough time today to take these with you. They'll be gross in your folders or wherever you keep your information. So that's why we need for sure our initials on it. Whenever you've done your measurements, over beneath this center area of the cabinets, you'll just lay yours here. And it'll be fully dry tomorrow for us. The next part on the back of the M&M directions are the marker and pens. You are just going to follow these directions. Okay? Now, here is the station to prepare the marker and pen inks. We are going to use the circular chromatography or filter paper. I already have pencils here and everything you need. So you is take the quarter and trace around it. Then there are 5 different marker and pens. And so, you're eyeing up about where the center is, totally fine. And then if we want to just equally space them, A, B, C, D, E, you can do in any order that you want. And then the pens and markers are there and will remain there. Please, if you take them back to your stations, then they're just going to get, going to make it hard for everyone to do the work. The individual markers and pens have letters on them. So how do I know what is E? Well, there you go. So all that you'll do, we only need one application. And as long as you can see the dot, you're good. So E, probably a little bigger. Good. And then I'll move to A and so on. You may have to kind of, press down. As long as you can see the mark, you are good to go. Next, you will, again, eye up where the center is and take this pencil or your pencil, and we're just going to poke a hole in the center. Also at the station are pieces of that circular filter paper that have been cut. I think it's best if you take this kind of pie piece, fold it, And then we are going to insert that through the filter paper. This will act as a wick. There is an empty beaker at your stations. You will fill the beaker with enough tap water so that when you set this paper in, the filter paper will come into contact with the liquid. And then the tap water will, through capillary action, rise and then move to be the mobile phase. You will let this develop until it's near the edge, about 2 centimeters. And I'll be around to watch and everything else to help. You can ask me anything. Make sure that we're also putting our initials on these. And what we'll do on the back of the procedure, you're not making measurements, we are describing. So if we want here, can we go ahead and change these to read A, B, C, D, and E? And then we are just going to describe. So for example, using my letter, if this were where I started, oh, well, G, there's no movement. If you did, then describe for me the color and then the approximate distance that it traveled. Do you want me to take a look at anything? Let me know. All right, so there were a couple things that were changed from the procedure. Remember, we want to be 1.5 centimeters. Phooey. You know how clumsy I am. Shoot, I broke your thing. Do not worry, I will replace, of course, and clean up. Shoot, I'm so sorry. That was a nice, crisp sound. I'm sorry, it woke you up. All right, did its job.
I wasn't asleep, but like,
woo!
Senses like, whoa.
All right. So, I have no idea what I was last saying. 1.5 centimeters. Oh, thank you. Abby, that made my month. That made my month that you were really listening. I know we do, sort of. No, not really. Sort of. In and out. We fade in and out, as was proven by my first period. They made so many errors because they weren't listening or reading or thinking. All right, anyway, Abby, that made my month. Thank you. 1.5 centimeters. The sodium chloride solution is already in your beakers. We are observing and measuring. And if we have time to calculate, if we don't, we'll finish that tomorrow. But there will definitely be time when the these are developing, and then the marker and pens are developing, and we're just kind of waiting. Page 4 of your unit packet. Page 4. And we take that opportunity to go ahead and practice naming and formula writing. If this isn't completed during our lab work, could you please do that for homework? So page 4. We are working with glassware and an alcohol solution and salt solution, so we definitely need our goggles. I am here to address any concerns that we might have. Go team.